What's the largest thing in the universe? It's a simple question, but the answer is almost impossible to comprehend. Not because we don't know we do, but because the scale is so vast that your brain simply can't process it. You can say the numbers, you can write them down, but you can't truly grasp what they mean. The largest known structure in the universe is the Hercules-Corona Borealis Great Wall. It's a filament of galaxy superclusters stretching across 10 billion light-years of space. That's not a typo. 10 billion light-years. That's more than 2/3 the diameter of the observable universe. It's so large that light traveling at 300,000 kilometers per second takes 10 billion years to cross from one end to the other. You exist on a planet 12,742 kilometers in diameter. The largest structure in the universe is nearly 1 billion times wider than your world. Trying to comprehend this difference is like trying to imagine the difference between a single atom and the entire Earth and then multiplying that incomprehensibility by 1 billion. But here's what makes it even stranger. According to the cosmological principle, one of the foundational assumptions of modern cosmology, structures this large shouldn't exist. The universe should be relatively uniform at large scales. Matter should be distributed fairly evenly. And yet, here's a structure so massive it violates that principle, challenging our understanding of how the universe formed and evolved. This is the story of scale, a journey from the familiar size of Earth through progressively larger objects until we reach something so incomprehensibly vast that it forces us to confront the limits of human intuition. Along the way, you'll encounter stars large enough to swallow our solar system, galaxies containing hundreds of billions of suns, clusters of thousands of galaxies bound together by gravity, and finally, the cosmic web, the largest scale structure of the universe itself. By the end, you'll understand not just what the largest object is, but what it reveals about the universe's structure, its history, and the strange fact that even on cosmic scales, matter isn't distributed randomly. It clumps, it clusters, it forms structures, and the largest of these structures is so big it shouldn't exist. Welcome to a journey through scale, from the world you know to the edge of comprehensibility. Let's start with something you can understand. Earth. Our planet is 12,742 kilometers in diameter. That's big enough that you've never seen it all at once, except in photographs from space. You can travel your entire life and never visit every continent, every country, every city. Earth feels vast because it's the largest thing you regularly interact with. But in cosmic terms, Earth is microscopic. Jupiter, the largest planet in our solar system, is 11 times wider than Earth. If Earth were a marble, Jupiter would be a basketball. You could fit 1,300 Earths inside Jupiter's volume. Standing on Jupiter's cloud tops, if you could somehow stand there without being crushed by gravity or sinking into the gas, you'd see a horizon so distant it would dwarf anything on Earth. The Great Red Spot alone, a storm raging in Jupiter's atmosphere, is wider than our entire planet. And yet Jupiter is tiny compared to the Sun. The Sun is 109 times wider than Earth. You could line up 109 Earths across the Sun's diameter. In volume, you could fit 1.3 million Earths inside the Sun. It's so large that it contains 99.86% of all the mass in our solar system. Everything else, all the planets, moons, asteroids, comets combined, is a rounding error. From Earth, the sun looks like a bright disk in the sky, small enough to block with your thumb. But that's only because it's 150 million kilometers away. If you could somehow transport Earth to the sun's surface, you'd find yourself standing on something so vast that its horizon curves away in all directions, impossibly distant. The sun's surface area is 12,000 times larger than Earth's. You could spend your entire life walking in a straight line across the sun's surface and never reach the other side. This is the beginning of the scale journey. Earth, which feels enormous to you, is dwarfed by Jupiter. Jupiter is dwarfed by the Sun, and the Sun, the most massive, largest thing in our immediate cosmic neighborhood, is about to be revealed as small. Our Sun is an average star, medium-sized, middle-aged, unremarkable in almost every way. And there are stars that make the Sun look like a grain of sand next to a beach ball. The largest known star is Stephenson 2 to 18, a red hypergent located about 19,000 light-years from Earth. Its radius is approximately 2,150 times larger than the Sun's radius. If you placed Stephenson 2 to 18 where our Sun is, its surface would extend beyond the orbit of Saturn. Earth, Mars, Jupiter, all would be inside the star, vaporized in the hypergent's outer atmosphere. Imagine that. A single star so large it could swallow the orbits of 6 planets. Stephenson 2 to 18 is so massive that light takes over 8 hours to travel from one side to the other. The Sun's light crosses its own diameter in about 4.6 seconds. This star is nearly 7,000 times wider. But even more mind-bending than its size is its density, or rather its lack of density. Stephenson 2 to 18 is so diffuse, so inflated, that its outer layers are less dense than the air you're breathing. If you could somehow survive in space and travel to this star, you'd pass through its outer atmosphere without immediately noticing. The gas would gradually thicken as you descended, the temperature rising, until deep in the core the pressure and heat would obliterate anything made of matter. These hypergents don't last long. They burn through their fuel at incredible rates, shining with the luminosity of hundreds of thousands of suns. Stephenson 2 to 18 has likely only existed for a few million years, a blink in cosmic time, and will soon explode as a supernova, possibly collapsing into a black hole. There are other giants, UE Scuti, VY Canis Majoris, Betelgeuse in the constellation Orion. Each one is hundreds or thousands of times larger than the Sun. If you lined up these stellar giants in order of size, the Sun would be too small to see clearly. Our star, which contains 99.86% of the solar system's mass and could fit 1.3 million, Earth's would be a dot. This is the scale of stars. And stars are just the beginning, because stars, even the largest ones, are tiny compared to the structures they form. Stars cluster together into galaxies, and galaxies are where scale truly begins to break your intuition. The Milky Way, our home galaxy, contains between 200 and 400 billion stars. Each one of those stars is a sun, many with their own planets, their own systems. The Milky Way is a disk about 100,000 light-years in diameter and roughly 1,000 light-years thick at its widest point. Light from the sun takes 8 minutes to reach Earth. Light from the center of the Milky Way takes 27,000 years to reach us. The galaxy is so large that entire civilizations could rise and fall in the time it takes light to cross from one side to the other. And yet the Milky Way is an average galaxy. Not particularly large, not particularly small. Just one of hundreds of billions of galaxies in the observable universe. The largest galaxies are elliptical giants, loaded collections of trillions of stars formed from the mergers of smaller galaxies over billions of years. IC 1101, one of the largest known galaxies, is about 6 million light-years in diameter, 60 times wider than the Milky Way. It contains roughly 100 trillion stars. If the Milky Way were the size of a coin, IC 1101 would be the size of a dinner plate. These giant elliptical galaxies sit at the centers of galaxy clusters, having gravitationally cannibalized their neighbors over cosmic time. They're the largest individual objects you can reasonably define as an object, a single bound structure held together by gravity, with a defined boundary where the galaxy ends and intergalactic space begins. But even galaxies like IC 1101 are small compared to the structures they form when they group together. Galaxies don't float alone through space. They cluster together, bound by gravity into groups and clusters containing dozens, hundreds, or even thousands of galaxies. The Milky Way belongs to the local group, a small collection of about 80 galaxies dominated by the Milky Way and Andromeda. The local group spans about 10 million light-years, 100 times the diameter of the Milky Way. But the local group is tiny compared to larger galaxy clusters. The Virgo cluster contains over 1,300 galaxies, spanning 15 million light-years. The Coma cluster contains over 1,000 large galaxies and thousands of smaller ones, spread across 20 million light-years. These clusters are held together by gravity, slowly pulling their member galaxies into chaotic orbits around a common center of mass. At the centers of large clusters, galaxies collide and merge. Over billions of years, dozens or hundreds of galaxies can merge into a single giant elliptical, creating the galactic monsters like IC 1101, and clusters themselves cluster into superclusters. The Milky Way, as part of the local group, is part of the Virgo supercluster, now more precisely called the Laniakea supercluster. Laniakea spans 520 million light-years and contains roughly 100,000 galaxies with a total mass of 100 quadrillion suns. Imagine that, a structure containing 100,000 galaxies, each galaxy containing hundreds of billions of stars, spanning 500 million light-years. The light from one end of Laniakea left when Earth was dominated by simple multicellular life, long before the first animals evolved. But even Laniakea isn't the largest structure, because superclusters aren't isolated. They're connected. When you map the distribution of galaxies across billions of light-years of space, a pattern emerges. Galaxies aren't scattered randomly. They're organized into a structure called the cosmic web. The cosmic web consists of vast filaments and walls of galaxies separated by enormous voids. The filaments are like cosmic highways, strands of dark matter in galaxies, stretching across hundreds of millions or even billions of light-years. The walls are where filaments intersect, creating sheets of galaxies. And the voids are vast, empty regions, hundreds of millions of light years across, containing almost no galaxies at all. This structure formed from tiny quantum fluctuations in the early universe. During cosmic inflation, random variations in the density of matter were stretched to cosmic scales. Denser regions had stronger gravity, pulling in more matter. Over billions of years, this created the filamentary structure we see today. The largest filaments in the cosmic web stretch for billions of light years. They're not physical objects in the traditional sense. There's no single structure holding them together. They're more like rivers of galaxies flowing along the contours of dark matter, the invisible scaffolding that makes up 85% of the universe's matter. And the largest of these filaments is the Hercules-Corona Borealis Great Wall, discovered in 2013 by analyzing the distribution of gamma-ray bursts, the brightest explosions in the universe, visible across cosmic distances. The Great Wall is a concentration of galaxy clusters and superclusters stretching across 10 billion light-years. To give you a sense of this scale, the observable universe is about 93 billion light-years in diameter. The Hercules-Corona Borealis Great Wall spans more than 10% of that. It's so large that it takes up a significant fraction of the visible cosmos. Here's the problem. It shouldn't exist. The cosmological principle is one of the foundational assumptions of modern cosmology. It states that on sufficiently large scales of hundreds of millions of light years, the universe should be homogeneous and isotropic. In other words, matter should be distributed uniformly, and the universe should look roughly the same in all directions. This principle is built into our models of cosmic evolution, our understanding of the Big Bang, and our calculations of the universe's structure. And it works beautifully at most scales. Zoom out far enough, and the clumpiness of galaxies and clusters averages out into a smooth distribution. Except the Hercules-Corona Borealis Great Wall violates this principle. At 10 billion light-years across, it's far larger than the scale at which the universe should become uniform. According to our models, the largest structure should be no more than 1.2 billion light-years across. Anything larger would require more time than the universe has existed to form through gravitational clumping. And yet, here it is. The Great Wall was discovered by mapping the distribution of gamma-ray bursts detected by the Swift satellite and other observatories. Gamma-ray bursts are the death throes of massive stars collapsing into black holes, visible across the entire observable universe. When astronomers plotted the positions of these bursts, they found a concentration far greater than random chance would predict. Follow-up surveys confirmed it. In a region of sky spanning the constellations Hercules and Corona Borealis, there's a vast concentration of galaxy clusters and superclusters, all roughly the same distance from Earth, about 10 billion light-years away. The structure stretches across such a vast region that it forms a wall-like distribution, a cosmic filament of unprecedented size. If you could somehow travel to this structure and look back at the Milky Way, you'd see our galaxy not as it is today, but as it was 10 billion years ago, when the universe was only about a quarter of its current age. The light we're seeing from the Great Wall left when the universe was young, before our sun existed, before our solar system had formed. The Great Wall challenges our models. It forces cosmologists to reconsider whether the cosmological principle holds at all scales, or whether there are structures even larger than we thought possible. Some researchers suggest that the Great Wall might not be a single coherent structure, but a statistical fluctuation, an apparent pattern in the distribution of gamma-ray bursts that looks like a structure but is actually a coincidence. Others argue that it's real, and that we need to revise our understanding of how large structures can form in the expanding universe. We don't have a definitive answer yet, but whether it's a true structure or a statistical artifact, the Hercules-Corona Borealis Great Wall represents the edge of cosmic structure. It's the largest thing we've found, and possibly the largest thing that can exist in a universe with the properties we observe. So what does it mean that the largest structure in the universe is 10 billion light years across? First, it's a reminder of scale. You exist on a planet 12,742 kilometers wide. The largest structure in the universe is nearly 1 billion trillion times wider. The gap between your size and Earth's size is nothing compared to the gap between Earth's size and the Great Wall's size. If you tried to build a scale model where Earth was the size of a grain of sand, the Hercules-Corona Borealis Great Wall would stretch beyond the orbit of Neptune. And that's conservative. The true scale is so vast that any attempt to represent it physically fails. You can only express it in numbers, and even then, the numbers are too large to internalize. Second, it reveals that the universe has structure at every scale. From particles to atoms to molecules to cells to organisms to planets to solar systems to galaxies to clusters to superclusters to the cosmic web to the Great Wall, there's organization at every level. The universe isn't a random distribution of matter. It's layered, nested, hierarchical. And this structure tells a story. The cosmic web formed from quantum fluctuations during inflation, amplified by gravity over billions of years. The filaments and walls we see today are the descendants of microscopic ripples in the fabric of space-time, moments after the Big Bang. The largest structures in the universe trace their lineage back to the smallest scales of quantum mechanics. Third, the Great Wall challenges our models. It forces us to ask whether we truly understand how the universe evolves, whether the cosmological principle is as universal as we thought, whether there are mechanisms of structure formation we haven't accounted for. Science doesn't progress by confirming what we already believe. It progresses by finding anomalies, things that don't fit, observations that force us to revise our theories. The Hercules-Corona Borealis Great Wall might be one of those anomalies, or it might not be. It might be a statistical fluke, an artifact of how we sample the universe, a pattern that looks meaningful but isn't. We need more data, better surveys, deeper observations to know for sure. But whether it's real or illusory, the Great Wall represents the limit of cosmic structure. Beyond this scale, the universe becomes smooth. There are no larger patterns, no bigger walls or filaments. The cosmological principle eventually holds. And in a strange way, that's comforting, because it means the universe, for all its vastness and complexity, is ultimately comprehensible. We can map it, model it, understand it. We can find patterns, discover rules, build theories that explain what we see. The largest object in the universe is almost incomprehensibly vast, but it's not infinite. It has boundaries. It exists within a cosmos that follows laws that can be studied, that yields its secrets to careful observation and rigorous thought. You are small, unimaginably, incomprehensibly small compared to the structures we've explored, but you're part of them. The atoms in your body were forged in stars that belong to a galaxy, that belongs to a supercluster, that belongs to the cosmic web. You're connected to the largest scales of existence by an unbroken chain of physical processes stretching back to the Big Bang. And somehow, despite being tiny, you can understand the vast. You can comprehend structures billions of light years across. You can map the cosmos, discover its largest objects, and ask what they mean. That's the true miracle. Not that the universe is large, but that something small enough to stand on a 12,742-kilometer planet can reach out with instruments and ideas and grasp the structure of everything. 10 billion light years. Try to imagine it. You can't. No one can. The human brain didn't evolve to comprehend distances like this. You evolved to navigate forests and savannas, to judge the distance to the next tree or the far side of a valley. A few kilometers was the edge of your world for most of human history. And now you know that there's a structure in the universe, a wall of galaxies, each containing hundreds of billions of stars that stretches across a distance so vast that light, the fastest thing in existence, takes 10 billion years to cross it. The Hercules-Corona Borealis Great Wall is the largest object we've found. It might be the largest object that can exist. And it's sitting out there in the cosmos, 10 billion light years away, indifferent to your existence, indifferent to Earth, indifferent to everything you've ever known. When you look up at the night sky, you're not seeing the Great Wall. You can't. It's too far away, too diffuse, spread across too much space. The individual galaxies that make it up are too faint and distant for your eyes. You need gamma-ray burst detectors, deep sky surveys, supercomputers analyzing millions of data points to even know it's there. But it is there right now. A structure so large it contains more stars than you could count if you spent every second of your life doing nothing but counting and lived for trillions of years. And here's what makes it profound. That structure, incomprehensibly vast as it is, formed from the same processes that formed you. Gravity, the clumping of matter. Quantum fluctuations amplified over time. The same physics that makes water droplets merge and planets form from dust also makes galaxies cluster into walls billions of light years across. The universe doesn't have different rules for different scales. It has one set of rules that applies everywhere, from the smallest quantum foam to the largest cosmic structures. Gravity works the same at every scale. Matter clumps the same way. The only difference is time and the amount of matter involved. You are made of atoms that were once part of stars. Those stars were part of galaxies. Those galaxies are part of clusters. Those clusters are part of superclusters. Those superclusters are part of the cosmic web. And that web includes structures like the Hercules-Corona Borealis Great Wall. You're not separate from these structures. You're part of the same cosmic story. The same initial conditions that created the Great Wall, created the Milky Way, created the Sun, created Earth, created you. You're a small, temporary, local expression of the same processes that create the largest structures in existence. Does that make you insignificant? In one sense, yes. You're incomprehensibly tiny. A speck on a speck orbiting a speck in a galaxy that's one of trillions, inside a supercluster that's one of millions, inside a cosmic web filament that's one of thousands. But in another sense, no, because you're the only part of this vast structure that knows it exists. The Great Wall doesn't know it's the largest object in the universe. Galaxies don't know they're part of clusters. Stars don't know they're made of atoms. You do. You're the universe that became conscious of itself. You're matter that arranged itself in such a way that it can look out at the cosmos, measure its largest structures, and comprehend, even if only mathematically, what it means for something to be 10 billion light years across. The Hercules-Corona Borealis Great Wall is the largest object in the universe. But you, small as you are the part of the universe capable of discovering that fact, pondering its implications, and feeling awe at the sheer scale of existence. That's not insignificance. That's a different kind of significance entirely. The universe is unimaginably vast, but it produced you. And somehow, against all odds, you can understand it. The Hercules-Corona Borealis Great Wall spans 10 billion light years, and it's just one structure in a universe filled with wonders we're only beginning to discover. Subscribe to Mr. Universe to explore them with me.